So let us start the assignment for week 9 sample. The first question of today is just I'm writing a true false condition and you have to comment whether it is true or false. So the statement is in an AWGN channel, the term white implies the power spectral density PSD is a constant function of frequency. Whether it is true or whether it is false. The answer is it's true. The term white means it affects all the frequency terms equally. All the frequency components of the signal, that is the input signal or the transmitted signal, equally. That's why it is true. Second question is a multiple choice question. It says if perfect recovery of a carrier signal is possible for both SSPSC and DSPSC, signals then the figure of merit of SSPSC is greater than DSPSC, lesser than, equal to DSPSC. Yes, the figure of merit is equal. for both DSPSC and SSPSC. Now let's go to the next question. So a signal that is going through a AWGN channel is passed. So let me write the question properly. That will be better. An AWGN contaminated signal is passed through a filter of bandwidth 50 megahertz. If the noise power in the filtered output is 20 nanowatt, then what is the value what is the value of two-sided noise spectral density? That is n naught by 2. Okay. The noise spectral density that is n naught is 20 nanowatt. But we are using a 50 megahertz filter. So this is n naught by 2, 10 nanowatt. This is the actual so after if we use a 50 megahertz bandwidth filter here like this, Suppose this is from 25 to 25 megahertz. This is total is 50. So what is the power contaminated in this region? That is N0 by 2 into the region 50. So that is 20 nanowatt by 2 into 50 megahertz. So this is a megaton 10 to the power 6 and this is 10 to the power minus 9. So if we do that, it will come as 2 into 10 to the power minus 16 watt Hertz inverse. I mean, this should be, as we have discussed, sorry, there is a point. I mean, this is like this megahertz. I have written there is the problem. So why this is like, this is 20 this is the whole term, this is the spectrum density, and this is the total region by which it is getting divided, total power. So that is 2 into 10 to the power minus 16 watt Hertz inverse. This is nanowatt and this is in megahertz. So this nanoterm contains 10 to the power minus 9 and this megahertz contains 10 to the power 6. So that is 10 to the power minus 15 and another 10 here. So 0 0 cancels out, 2 2 cancels out, 1 by 5. So that's why it is 2 into 10 to the power minus 16. And this was the power of the output. I think it's clear for everybody, because the total power is 20 nanowatt and we are doing only 50 megahertz here. So that is the total 20 nanowatt by 2 one-sided, because of it we have done for the both sided, so that's why divided by 2. And the total region is per hertz. What is per hertz? That's the power. So the output of this region is actually 20 nanowatt here. So what is the PSD per hertz? That sort of thing. So the bandwidth is 50, power is 20 nanowatt. So 20 nanowatt by 50, and for one sided, that is both sided, so that is divided by 2. That's the reason. So 2 to the power minus 2 into 10 to the power minus 16. I just miscalculated it in the first instance. Sorry for that. Okay. Let us go to the fourth question. Fourth question says, in a receiver, the power of an input signal is 50 microwatt, while the power of additive noise is 20 microwatt. So the signal plus the noise is passed through a filter, and the characteristics of this filter is simply an amplifier. So what happens, this signal plus noise is goes through a amplifier of factor 20. But what happens, we are sending the signal plus noise to amplifier, and this amplifier is also adds a sort of noise. And the power of that noise is 100 microwatt. So the question is, what is the final SNR? That is the output of this box. So let me draw the picture for clear reference. So as input signal that has IP, it is going through an antenna that adds up. So this has a power of 50 microwatt, and this, whenever we are receiving it inside an antenna, this adds up a noise of 20 microwatt. So there is a resultant signal, and this resultant signal is again going through a power amplifier. And this power amplifier has a factor of gain 20. However, it also adds another noise of 100 microwatt, and there I will get a signal SNR. So this power is 50. So here the input signal power is also 50, and it is getting multiplied by 20 times. So that will be 1000 here. So this is 20. Because this 20 microrod is here and this 20 getting multiplied by 20 plus another 100. So total is 500 microwatt. So SNR that is 2. So SNR is 2, the ratio. Is clear for everybody, I think. Question number 5 says, consider the message signal is DSPSC modulated. And is transmitted in baseband through an AWGN channel with two-sided noise spectral density So if the signal MT is transmitted such that it possesses same power So what is the SNR? The question once again, there is a message signal MT, that is a sync function, and it's DSPSC modulated, and then it is transmitted through a baseband of, that is AWGN channel with two-sided noise spectral density that is given N0 by 2. So if the signal MT is transmitted such that it possesses the same power as the modulated signal and is passed through a low pass filter of the bandwidth of same bandwidth of MT, so that other components does not arrive in this sense. So what will be the SNR in that case? So the message signal MT is sync of pi t of 2t. So what will be the aim of f, that is the Fourier transform of this, is 1 by 2t direct f by 2t. So for this signal, from Parseval's theorem, applying Parseval's theorem, it is easier to calculate the power, signal power, from this here is point to infinite df for this direct signal, and it will be 1 by 2t. This is the power of the message signal. Right? So we can say power of the MT is 1 by 2t. So after we do some DSPSC modulation, the power will be 1 by 2t into half, that will be 1 by 4t. Again, the bandwidth of the message signal is t, because this is f by 2t. So SNR will be 1 by 40 into n naught t. That is 1 by 4 naught t square. This is the bandwidth. Okay, I've written already. So once again I'm explaining what we have done. From empty we have done the Fourier transformation, and the Fourier transform is a direct signal. So applying Parseval's theorem, we can get what is the power of the message signal. That is 1 by 2t. So again, as we have done the DSPSC modulation, this signal power will be divided by 2, 1 by 4t, and then the bandwidth of the message signal is t. So noise will be collected under only this region t. So t into the n naught, that is the total noise power. So n naught t. So this is the noise power, 1 by n naught t, and this is the signal power. So signal by noise is equal to this 1 by 4t by n naught t. That we have calculated as 1 by 4 n naught t square. Anybody has any doubt about this question? Okay, let us go to the next question then. Says consider a bandpass noise that is nt is equal to 2ni t cos omega ct minus 2nq of t sin of omega ct, where this ni and nq are independent baseband baseband process each with power P. Then what is the power of NT? Okay. So the answer is these two components are independent. So basically the power will be add up for both of the components and each with power P. So first one is power will be 2 times the NIT, right? So power of NIT is P and this is 2 square plus similarly 2 square into P. Because it's squared up because this is power. The amplitude is 2. So when we calculate the energy or power, it will be just square of that. So that is 4P plus 4P by 2 by 2. Why this by 2 factors comes? Because there is a cos component and a sine component. So total power will be 4P. Question number 7 says a certain telephone channel that is Hc of omega is 10 to the power minus 2 over the signal bandwidth. So this gives a gain of 10 to the power minus 2 over the region where the message signal contains. Now the message signal PSD is Sm of omega is equal to beta rectangle omega by 2 alpha, with alpha equal to 4000 pi. The channel noise PSD is n of omega 10 to the power minus 8. If the output SNR at the receiver is required to be at least 30 dB, then what is the value of beta? Corresponding to the required minimum transmitted power. Okay, let us solve this one. So key thing we have to remember that we need a SNR that is of 30 dB. So what is 30 dB? That is the gain of 1000. So this means the signal we receive by the noise power, that should be 1000. Or what is this S0? S0 is the input signal that is going through this telephone channel. hc of omega. Write clearly, hc of omega by n naught square, because hc was the channel gain. So when we are calculating the power, we should take the mod square term, and this should be also 1000. So basically this signal is going through this channel, and if we multiply these two, it will come S naught. That S naught is this, and this should follow this condition 1000. Now what is the N naught? N naught is 2 B. So that is 2 into what is the channel noise PSD is 10 to the power minus 8. So that is 10 to the power minus 8, and the B is the bandwidth. So what is the bandwidth here? Is 2000. So why B is 2000? Bandwidth is alpha by 2 pi. Right? Because this is 2 alpha, and alpha is 4000 pi. So that is why this is 2000 hertz. So basically this is the bandwidth of the message. So we should consider only same bandwidth, that is between message and noise. What noise component is exactly affecting these message signals? So if there is some noise that is out of band of the message signal, that does not play any role, because that component is something else. We only have to consider what noise component is going to affect the message component. So that is the same shared frequency band. So that's why what is the message bandwidth is 2000 hertz. Noise bandwidth, for calculating noise power, we will also use the same frequency band, that is 200 hertz. So this is the N naught. Similarly, when we are going to calculate the input signal power, that is SI, that is beta from this equation, direct signal in the frequency domain. So beta into 2 into 4000 pi and divided by 2 pi. So that is equal to the signal power. So what we need now, we have to match the equation SI into hc of omega square by N naught should be equal to 1000. So SI we have here, N naught we have got like this, and HC mod of HC omega square, that is 10 to the power minus 4, because it is given here. if we calculate all these things from these, we can get that beta equal to 10. If we substitute all these things and compare with the right hand side, the value of the beta will come 10. I think it's clear because see, just do the calculation. Into this will be 2 cancels out, pi cancels out, 4000 into 10 to the power minus 4 by this will be 4000 into 10 to the minus 8. This should be 1000, or beta should be these two cancels out. Just a minute. I think we are doing some wrong calculation here. Fundamentally this is the correct way, but I have to check this question once again. There are some wrong calculation I think in the given solutions. So I will check this question once again. There are some calculation mistakes that has been done in the paper. Okay, just leave this question for right now. But the fundamental thing is clear, right? So you have to think about what is the message signal, what is the gain of this channel, the message signal, and from there this part you can know what is the actual bandwidth of the signal, and that has been given with alpha factor, and channel noise is also given. So whenever somebody is asking you to calculate some SNR such that you have to maintain some certain limit, so start with this criteria first, that SNR should be 30 dB. So that is 1000, gain of the 1000. So the first thing is the output message signal power and output noise power is 1000. So that is the criteria, and here we have given what is the beta, but amplitude beta is the key factor that we have to find out. So that's why we first calculated what is the noise power, that is within this band, what is the noise power, and also what is the input signal power was there, that this 10 to the power minus 4 it was here, and this SI was the input power. So that is the input power, this is the channel power. So output power is multiplication of both of these. So this signal is going through this particular channel, so that's why this is the output power. That is input into the channel by the output noise power. That has to be 1000. That is the criteria here, I think. But I am missing something here probably. So after that you have to write that SI should be equal to this factor, and you have to calculate that. Just give me 2 minutes. I'll just check one. I will just check it once again. Okay, let's leave this question for right now. Let us go to the question number 8. So this says there is a DSP-AC signal that is transmitted over a noisy channel. So let me draw the signal first. That is from minus 400 to 400. And this is 10 to the power minus 6 watt per hertz, as it is the power spectral density, F kilohertz. So the thing is given, the message bandwidth is 5 kilohertz. And the carrier frequency is 100 kilohertz. So if the average power modulated signal is 100 watts, then what is the SNR at the receiver? So again, a DSP-AC modulated signal is transmitted over a noisy channel, and this is the PST of the noise. Now the signal bandwidth is 5 kilohertz and carrier frequency is 100 kilohertz, and the average power of the modulated signal is 100 watt. So what will be the SNR at the receiver? That is the thing you have to calculate. So just a small change here, 0.75 to 10 to the power minus 6.
So the particle density is 75 into 10 power minus 6, is it?
0.75 into 10 to the power
Oh,
minus
0.75. Okay.
So basically what is the answer coming? I have not calculated this one, but fundamentally what you have to do, I'm just telling you. You have to calculate power in this region, that is of at least 8 kilohertz. And then whenever you are calculating the SNR, you have given the average power of the modulated signal is 100, specifically with respect to the noise power. Sorry, the noise power. So what is the noise? How to calculate this noise power? This is a triangle, and this is another triangle. So if you want to calculate the noise power, that is over this total 8, calculate the area under this triangle. That will be the noise power. That is over is 8 0.8 800 frequency band, 800 hertz. Sorry, this is wrong. This 800 hertz, and the peak value is also given. So it is easy to calculate what is the power under this region. That is the noise power in the receiver. Then you have to put this noise bar here, and it is already given that the average power of the modulated signal is 100 watt. So just divide that 100 watt by this average noise power. Then the SNR at the receiver you will get. The only task here is to calculate the noise power from this curve. As the peak value is also given. This is like half into 0.75 into 10 to the minus 6 into 400. It is for one side, and you have to multiply it by 2 times.
Sir, can you explain question 8 again, please?
Okay. So the question 8 was like, I don't think it will come back. You had a DSP-AC signal, and this signal is transmitted over a noisy channel. The message bandwidth is 5 kilohertz, and carrier frequency is 100 kilohertz, and average power of the modulated signal is 100 watts. So basically what was given there, alpha, suppose this is the level alpha, and this was like minus beta to beta. Just take it. And this is the noise PSD. So the question was asked, what is the SNR at the output? So basically what we have to do, it was given the carrier frequency is 100 kilohertz, The average power of the modulated signal is 100 watts, and it is for DSPSC signal. So that is already suppressed carrier. So this average power of the modulated signal is 100 watt. So basically we can think of the message signal is of nearly 100 watt. The signal power is given 100 watt, and then PST of the noise is also given. Suppose this is alpha and beta. So from this, as it is the PST, you can calculate the noise power from the PST. This is the total frequency band. It will be given in the question, and the range will be given. So basically for this, what will be? This is 0 to beta. So this is the area under this triangle. You can calculate as half into alpha. This is the height into beta, the area under this triangle. Similarly, this you can find this area under this triangle also. So that is also another half. So that is calculated by 2 into half into alpha beta. So that will be alpha beta. So that will be the noise power in this region. So signal power divided by, you have to calculate the noise power under this alpha beta. And you have to think, with this message bandwidth has 5 kilohertz. So at least this range should be 5 kilohertz. If there is something beyond this 5 kilohertz, you have to omit that range, because you have to only consider the message bandwidth. So if the if 2 beta is beyond the message signal, that can be like 2 beta is greater than 5 kilohertz, then you have to take the region that is only under the 5 kilohertz. Suppose this region is only under 5 kilohertz. So that is the region where noise affects this message signal. So you have to think about only this part. But only the problem here, the only sample solutions are given, there are some numerical mistakes. So that's why I'm not telling what is the actual answer. But that is the motto, that you have to calculate what is the noise PST under the bandwidth under which the message signal is being transmitted. And it is stated that it is a DSPSC signal, suppressed carrier. So basically the average modulated power is 100 watts. So we can calculate it as the signal power. So that is the SI by noise. This is the noise power. So that is the only thing you have to do. Is it clear now a little bit?
Yeah, it's fine now. Thank you.
So consider a DSPSC signal that is going through a coherent demodulator. whose local oscillator suffers from a phase error of theta. So the message signal, that is MT, has a bandwidth of B and power of P. Channel noise PSD is N0 by 2. So what is the output SNR? So once again, a DSPSC signal that is going to a coherent demodulator with local oscillator. So as there is a local oscillator, it can suffers from a phase error of theta. And now the extra information that is been given, that message signal is MT with a bandwidth that is B and power P. And also the fact given is channel noise PST, that is N0 by 2. So what will be the SNR at the output? Okay, let me solve it. So only fact that is given, that phase error of theta. So this model, we can think that the actual message signal that is getting multiplied a factor of cos of theta. So what is the output will be? That is xt is equal to, suppose, m of t of cos theta, as there is a phase error of theta, plus there will be noise components. So noise will have an in phase component, that NIT, and it will also get a phase factor of theta. Similarly, the Q phase component, it will also get a theta, but this time it will be sin theta. So this is the received output. Message signal multiplied a phase factor theta, and noise has two component, Ni and Nq. This has cos theta component, and this will be have sin theta component, because this is the quadrature phase. So the received output will have a power that will be equal to, suppose this MT has a power P, and as there is a half term comes here, that will be by 4, and this will be cos square theta by, this is the noise term. So we don't have to think about this for right now, because we already has given this is the channel noise PST and not by 2. So this is N0 by 2 over the bandwidth B. This is B. So this will be T cos square theta by 2 n naught b. So this part has a power of n naught 2 by b, and this is the power of this part. This is the power of this part. So SNR will be this. Okay. So let us move to the last question of today. This says an unmodulated carrier of amplitude AC and frequency FC is added to band limited white noise. And then it passed through a envelope detector. But the key is this does not have a DC blocker. So additional thing is given, the noise spectral density, noise PSD is n naught by 2 and bandwidth is 2W. That is centered about carrier frequency FC. So what is the SNR? So again, unmodulated carrier of amplitude is given AC, frequency is given AC, FC, and this is added to a band limited white noise. And so after that it goes through an envelope detector that does not have a DC blocker. So this signal and band limited noise is getting added with this unmodulated carrier signal, and then it passes through an envelope detector and with a DC blocker. So after that additional information is given about noise PSD, that is n naught by 2, and said that it also bandwidth of the noise, and it is said this structure is centered about the carrier frequency FC. So what is the SNR? The output. Also one extra information you can think, that is carrier by noise this ratio is very high, greater than 1. Okay, so let me solve it. So what is the unmodulated carrier here? Amplitude of AC and frequency of FC. So we can write it as AC amplitude with a carrier cos 2 pi fct. Then it is getting added with a band limited noise of NT. So the resulted signal we can write as AC cos 2 pi fct plus the noise term NT. Now we can write it also like this, cos 2 pi fct, and this noise has a in phase component and quadrature phase component. So if we write in that term, that is NIT cos 2 pi fct, and also the quadrature phase NQT sin 2 pi fct. So this AC and NI can be added as the amplitude here because they contain the same cos.
So NQ of T will have a negative sign, right?
Oh, yes.
Yeah.
It's a mistake.
Yeah, thank you. Thank you.
This will be cos 2 pi fct, and this will be NQT sin 2 pi fct. This is the total signal. So when it goes through a envelope detector, what envelope detector does, it applies a capacitor and it just try to uh, demodulate it based on this amplitude. So first of all, we we just try to get what is the envelope sort of thing. So what will be the envelope of this sort of signal in the envelope detector? So that is AT, we can think that is sort of this term, x square plus y square in the envelope detector. So that will be AC plus NIT for the cos term plus NQT square. Now when this AC square by the noise power that is given, that carrier power by noise power is greater than 1, we can neglect this part because it will be very small term, but this term contains AC plus NIT square. So this will be the main term upon which this envelope will detect, will be changed with respect to time, because NQT will be is coming from a noise, right? And AC is a carrier carrier amplitude, and it is given that this carrier power is very greater than this noise power. So if this situation occurs, this NQ term will not have a very significant term rather than this term. So we can rather write neglect this NQ term, and we can write that AT, the envelope of xt, that is AT, only depends on the term this AC plus NIT square. So basically we can write it as AC plus NI of T. Again, there is no DC blocker in the envelope detector. So this AC term will easily pass through. If this DC blocker was there, then this AC term will not pass through. So the output signal power is mainly coming through this AC square. Right? And what is the noise power? When we are going to calculate the noise power, we have to take what is the noise spectral density n naught by 2, and what is the bandwidth 2W, centered about this frequency band. So the noise power will be 2 into n naught by 2. Sorry, this n naught by 2 into the bandwidth 2W. So that will be 2n naught W So the SNR is carrier power by this noise power. Okay, it is clear for everybody, I think. Okay, someone asked that 30 dB question, but I think that 30 dB question there are some mistakes. So which one 30 dB? Just let me check it 1 second.
Sir, can you repeat some mistakes you were telling? No, what is that?
Yeah, there are some mistakes that are given in the solutions itself. So basically, it is asking for
Solution, sir?
information. There are some mistake for question number 8 that I have told you in question number 7.
Question number 8 of which assignment, sir?
it will be like it will be for assignment 9. I don't know what is the actual solution for the actual, like in this semester there will, the question could be modified, and
Okay.
whatever the solution that is given for the previous semester,
Okay.
there are some mistakes I think. So there are no conceptual mistakes. All the
Okay,
mistakes are
no, but
the.
mistaken answers, even I felt because some question on amplitude modulation. Okay, so even I felt. Anyway, you had told we'll have a special session in the second week of October. I will post that question, sir.
Okay, okay. So yeah, you can
Okay, I'll do. Can
complete
I
it.
do that? Okay.
Yes, yes.
Yeah, okay. Yeah, thank you, sir.
Okay. So this was all for today. We'll meet in the next Sunday.